Okay, hello again, everyone. I hope you enjoyed the great keynote by Sean. And we are back to the track A. So this is track A. This is Paolo's talk about WebAssembly. Ciao, Paolo. How are you doing today?
Ciao, hello.
Hello. You are from you are there in Seattle right now,
I'm in
right?
Seattle, yes. I'm in Seattle.
Nice,
It's
nice. It's
a bit
early in the
late
morning.
here, or very early. I'm not sure.
It's a bit early, probably. Yeah.
Yes.
Well, yeah, it's not very early there. Yeah, so it's early here. It's kind of midnight, maybe there, or.
It's 1:45 a.m.
Okay. So yeah, it's a bit early or late, probably. It
Yes.
depends on. Nice. So, Paolo, I leave the stage up to you,
Thank you.
and we'll get back for the questions. Feel free to ask about me anytime. I'll be here behind the scenes.
Thanks.
Great. Thanks. Enjoy everyone the session by Paolo.
Okay, let me start. Hello, everybody. So I am Paolo. I work in Microsoft in the team that develops the Microsoft Edge browser, and I'm very passionate about WebAssembly. So I am pretty sure that you already heard of WebAssembly. This is a conference dedicated to C++, and so probably this is a technology which is not unknown to many of you. But WebAssembly is a technology that allows people to run code written in C++ or in other languages in a web page. This it's important because web browsers are a wonderful invention, but they have the defect or the quality, according to somebody else, that they only run JavaScript code. And WebAssembly is a way to overcome this limitation. And in this talk, I will not focus so much on the history of WebAssembly. We will see a little bit how we can compile and run WebAssembly code. And more focus will be on how WebAssembly works under the hood, how a WebAssembly engine works. So, WebAssembly. A definition, good definition that I found is WebAssembly, or Wasm, as it's also called commonly, is an efficient, safe, low-level instruction format for a stack-based virtual machine. And it is like machine code for a virtual machine, like a virtual instruction set for a virtual processor. So the idea is that if a browser implements the runtime to support this instruction set, then we can compile from source languages like C++ or Rust, targeting this instruction set, and this will work also in a web browser. This is being developed as a WTC standard, and it is supported by all major browsers. And it's also, very interestingly, used more and more also outside the web. And we'll talk also a little about this. And before going into the details of WebAssembly, a few words about the real-world adoption of WebAssembly today. So these are just 4 examples that I found because I found they were meaningful. For example, Google Earth is a very nice application with 3D graphics, and it's made with JavaScript, and also WebAssembly probably to speed up the graphics with WebGL. Then there is Blazor, which is a Microsoft technology to run .NET code in the web page. And this works because the mono .NET runtime has been ported to WebAssembly. An interesting example is Wikipedia, because it shows that you don't have to compile the whole application to WebAssembly. You can just use it for a small component in your web application. For example, Wikimedia had the problem that they wanted to use specific codecs in the past, and these codecs were not supported by all browsers. So they use WebAssembly to implement a codec with a good performance for the browser where these codecs were not supported. And another example is AutoCAD, which is an example where a company has a a product with a lot of legacy C++ code, and they want to port at least part of this code to the web, and WebAssembly is perfect for this. And also Adobe, I know it's ported Adobe Acrobat, for example, and so this is a common usage. And these are examples that are all web-based, but as I was saying, WebAssembly is also used outside the web. And an example is Fastly, which is which produce software for edge computing and content delivery networks. And Fastly is one of the companies that is more behind the evolution of WebAssembly today. And then there are other use cases like video games, emulators, and unfortunately, a very common use for WebAssembly is also Bitcoin mining. It's very frequent that there can be WebAssembly code doing nasty stuff under the hood in web pages. But yeah, let's look at how we write WebAssembly code. So, not by hand usually. There is somebody who's able to write WebAssembly code, WebAssembly programs just by hand, but normally it would be like writing a modern application in assembly. Nobody does that. There are many tools to generate WebAssembly code, but as far as I know, in the end, all these tools rely on the LLVM toolchain. And well, there is probably no need to talk a lot about LLVM in a C++ conference. You probably know that it is a compiler infrastructure written in C++ that has a very modular architecture. And so everybody can provide the front end for a new language. For C++, the front end is Clang. Front end transform the source language into an intermediate representation, and there are optimization algorithms that run on this IR. And finally, the resulting IR is fed to a backend. There is a different backend for different architectures, and so the backend for x64, for example, will generate x64 code. And for WebAssembly, what they needed to do was just to add a new backend for this new architecture. It's a virtual architecture, but it's an architecture in the end. So this is a very simple example. What happens when we compile a C or C++ function to WebAssembly? We can just use Clang. We don't need to use any other tool chain. It's already, Clang already supports generating WebAssembly code as a target. This works in simple cases. And so in this case, compiling with this command line, we would have a new file, calc.wasm. So we have in this file, this is just a calculator that computes some operation on two operands based on the operation code, but it's trivial. But so we will have this module, and we can observe this module. Let me open the browser. So with tools like there are command line tools like Binarian. There is this nice web tool, WebAssembly Code Explorer. Have already compiled this calculator module, and you see this is the shape, the structure of a module. It contains a number of sections, export sections, code section with functions. In this case, we have one function. And there are globals, there is a memory, and we'll look more in detail how this works. An interesting thing is also that we can use the Godbolt Compiler Explorer also to generate code in real time and see how the code for a C++ function, what is the Wasm code generated for C++ function. So this is, for example, what Clang generates for this simple function. But let's look more in detail at this code. If I find, sorry, right one. Yes. So this is the code in the code section for this module. So we see that the source code had a switch case and with a couple of branches. And what we see as a result is a function with a signature and instructions that are similar to assembly code, but not quite. There are some differences because the WebAssembly works with a typed stack machine. So, for example, these are the 3 instructions to compute the multiplication of the 2 operands from the function that we saw before. And what happens with this code? So there is an execution stack, which is where we call local get P1. What we do is to push the value of P1 into the stack. P1 is a local. What is called a local is actually one parameter of the function. And these locals in WebAssembly are like virtual registers for the Wasm architecture, and there can be any number of registers in a function. And so we push the value of P1. With the second get, we push the value of P2. And at this point, the stack will have 2 slots that both contains 64-bit floating point numbers. And the typing is important because all these slots have a precise type at any instant. And so, for example, the next instruction, the F64 multiplication, will expect that there are 2 F64 elements in the stack, and will pop them from the stack, will calculate the result, and will push the result to the stack. But what happens if instead the type does not match? For example, there is an integer. Then there will be a validation error. The interesting aspect of WebAssembly is that this check can be done statically when the module is instantiated, before the code runs. And so the module can be statically checked for type validity, which is one of the security elements of WebAssembly. And the other particularity of this WebAssembly code is that there are no goto statements, but the language defines control flow structures like blocks, loops, branches, ifs, and so on. So what happens with a block like this is that a branch can move the instruction pointer either just after one of the blocks or back at the top, the beginning of the block, but it cannot jump at any random offset in the code or any instruction offset. It has to be at precise points in the code. And this is also part of the type safety of the language. How do we run WebAssembly code? So WebAssembly runs needs a runtime. And the runtime in web browser is represented by the JavaScript engines. So for Chrome and Microsoft Edge, the engine is V8. For Firefox, is SpiderMonkey. For Safari is JSC, JavaScript core. And all these engines also support WebAssembly together with JavaScript. And there is a JavaScript API that is defined by the standard, can be used to load a file, compile a file. This will generate a module, and the module can be instantiated one or more times, and as part of the instantiation, we will define the imports and the memory for this module, and we'll see this later more in detail. And this is on the web. But server-side, there are other engines. There is, for example, Node.js, which is also based on V8, but there are engines that are completely different, like Wasm Time, which is oriented to Rust especially, and it is an engine that does not even support JavaScript, I think, and it's used to run very quickly Wasm code server-side. And there are many other engines like this, and there are even micro engines designed to run WebAssembly on IoT devices. From the point of view of security, an interesting aspect is that WebAssembly has what is called a hardware architecture, where the program state is separated from the code. So basically, code and data live in separate memories in WebAssembly. For this reason, a WebAssembly program cannot modify its own code or the code stack. It can only access a so-called Wasm memory object, which is shared with the host environment. So there is like a division between a trusted environment sandbox, Wasm sandbox, where the WebAssembly engine runs and where there is the WebAssembly instance, the generated code, and the execution stack, and the untrusted application state, which uses this WebAssembly module. And the only thing that is shared between these two worlds are the memory, which is visible as a JavaScript array buffer or shared array buffer, and then the other things that are shared are the functions that the Wasm instance imports. So there is this import section in the module that defines which function this module needs to run. And these functions must be provided by the host. In this case, for example, functions foo a bar must be provided at instantiation time by the host code. At the same time, in the export section, a module defines which functions are visible for the host code. So which function can be called, for example, the function calc in our example. And the fact that there is this separation means that some vulnerabilities, like the ability to modify the content of the stack, are not possible with WebAssembly. So things like the return-oriented programming that it's used by code vulnerabilities when there is a bug, this doesn't work with WebAssembly. So there are certain kind of attacks that are not possible. In this way, WebAssembly, it's like a sandbox. It's quite safe by default, which doesn't mean that there cannot be bugs in the engine itself. And actually, the script engines, the WebAssembly engines, are very critical from this point of view. And often they open the door for attacks to the browser. But in itself, the architecture is very safe. So what can WebAssembly do? Well, Ben Smith, in a talk, said a very interesting, funny phrase: WebAssembly cannot do anything, which is true, because as we saw before, by itself, the only thing that WebAssembly code can do is to write into the memory, and it cannot interact with the external world in any other way, unless explicitly some function is passed to have some interaction with the external world. So host code can only call WebAssembly functions that are explicitly declared in the export section, and Wasm code can only call external functions that are explicitly passed in the imports when a module is instantiated. And so WebAssembly by itself cannot render graphics, cannot play sounds, cannot access the DOM, cannot read the file system, cannot open HTTP request, send a HTTP request. But it can do all these things through functions, normally JavaScript functions that are passed in the import at instantiation time. Now, this is a very small example, very trivial example of a function that takes a string as input and does some computation and returns a value. And in this case, it decides if the string is a palindrome or not. But this example is interesting because it shows us a few things. How do we pass complex types like strings or pointers to a JavaScript function? How the JavaScript function can call an imported function, and how do we call, how the code uses standard libraries, how does it work? Let's see. Let's start with the memory. How do we pass pointers to WebAssembly? So if we look at the signature of the Wasm function that is compiled, it is generated by Clang. This is palindrome. What was originally a constant star becomes an I32. So the pointer has become an integer. Why? Because we saw that the Wasm function can only accept a few basic types as arguments. Actually, don't know if I mentioned this, but yes, the only basic types that are valid arguments are integers or floating point numbers of 32 or 64 bits, and that's all. There is no way to pass a string, there is no way to pass a reference, a class, a pointer, that's all. And we also saw that in WebAssembly, the memory is separated from the stack, from the code. However, when we have a C++ program, we expect that this program will use a stack for its internally to call other functions, to allocate local variables, and we use a heap to allocate objects and so on. And however, this stack is different from the execution stack of WebAssembly. This is this, let's call it C++ stack for the execution of C++ code. And this C++ heap stack are actually in the Wasm memory object, which is the object. This is the memory that is shared between the WebAssembly code and the host. And the memory layout here is determined by Clang and by the linker, and more or less is like in figure. There is initially a static data segment where the data section for the module is copied at the instantiation time, and then the rest of the memory is divided between a C++ stack and the heap. And if we want to pass a string, so what we need to do is to copy the content of the string into the memory and to pass the index of the initial location of the memory. There is no standard way to pass complex types to a WebAssembly function. WebAssembly code and this code must agree on a serialization format. So, for example, we have decided that this serialization is a sequence of characters, and the pointer to an object is passed as the index into the memory array for this serialized sequence of bytes. For example, let's look at how we could have this working in a web page. So this is our original code. We have compiled it to Wasm, and then we write a small HTML page to test this functionality. We see that there is an API to load the module and to compile and instantiate an instance. When we instantiate the module, we know that the module expects a function log, actually, and this function log is implemented here in JavaScript, and it's passed in the import object which is passed to instantiate. So, and we implement this, for example, logging to the console. And the other thing that we saw is that there is a memory object that is part of the definition of the WebAssembly module, and that can be mapped into this memory object can be used as a buffer for a typed array in JavaScript. And we can also call the function that is exported by the module, which is, in this case, is the function is palindrome. So with this preparation, when we want to check if the string is palindrome, what we can do is to manually, for example, copy the content of the string into memory. This is very ugly code. Nobody would use code like this, but it's just to show how this could work. We can decide an offset in memory. We can copy the code character by character in memory, and then we can pass the offset of this string to the function. And if we try this, it should actually, let me remove. This should be for later. So if we try this, it doesn't work. It should, but we can see why. Yes, because I changed the name of the control. But anyway, I don't know if there is time to fix this very quickly. So yes, we said that this is called console log. Actually, that's why. And then if we reload this, remove this, try again. Yes, now it works. This doesn't work. This is not palindrome. Okay, so this is to show how we can pass an object, but this is just an example. This is not how a real program would work in reality. Obviously, we cannot work in this way. There must be a better way, and we need support from the compiler toolchain to do this binding between JavaScript and WebAssembly. And for this, the best tool is Emscripten. Emscripten has a long story and is actually older than WebAssembly itself. Originally, it was created for SMJS, which is another JavaScript technology to compile C++ code and run it on the web, but it's a different story. And now it's obsolete. So Emscripten is a great tool chain to generate WebAssembly. It's also using Clang under the hood, but it provides a lot of functionalities to port existing C++ project to WebAssembly. It provides support for C++ standard libraries and for other kind of libraries like multimedia libraries, graphic libraries, OpenGL, SDL for audio, WebSockets, also a virtual file system, and Emscripten, it can be used both for the web platform and server side, but it's particularly used with the web platform. And the backend for this API is provided by the web platform APIs, like, for example, calls to OpenGL are translated into calls to WebGL so that the application can work in the browser. Calls to SDL for the audio are translated in calls to the Web Audio API, and so on. Calls to WebSockets are managed through the Web API. And the file system is actually only a virtual file system because you cannot access the file system from the web platform. And besides that, Emscripten also provides C++ JavaScript bindings with a technology called Embind, and it also provides all these serialization mechanism for complex types. And to do all this magic, mscripten generates also a lot of JavaScript code, JavaScript glue code that acts as an interface between WebAssembly and the JavaScript host application. But all this mscripten stuff, let's say, is works very well, but it's implemented in its own way. It's not standard. It would be better to have a standard mechanism to define an interface with the operating system and with the system libraries, and for this. WASI has been developed. WASI, WebAssembly System Interface, defines a standard API to interface WebAssembly with operating system, and this is especially useful when running WebAssembly server-side. So far, WASI provides APIs for file system sockets, process scheduling, standard libraries, and it is also being standardized by the WTC, and it is still under development, but it's already supported by Clang. So, for example, the program we saw before, instead of with mscripten, could have been compiled with Clang directly, and just setting Wasm 32 WASI as, WASI to as target, and specifying what is the sysut, what is the folder to be used to find, include files and libraries for the compiler. And this works with server-side engines like Wasm Time that have already the support to connect WebAssembly with the operating system to WASI, and it doesn't work by default on the browser. So this module that we would compile with Clang will not load on the web page because the browser does not have yet the WASI mechanism to the WASI interface, but it's possible to make this work with the JavaScript polyfill, which emulates basically what is needed by WASI. Now, as we saw that by default, WebAssembly can only accept a few basic numeric types as arguments in functions, and this is not ideal. And so one of the proposals that is being worked on is to add Wasm interface types, so a mechanism to extend the type system and pass compound types like vectors and strings to functions. And this should be the base for the definition of Wasm interfaces in the future. But I'm not really an expert on WASI, to be honest. I'm work more with the mscripten. And so I would like to talk a little about what we need to do when we want to port real big application to WebAssembly. So mscripten generally works quite well for this. And normally, code that compiles with Clang and that only uses POSIX APIs also compiles with to WebAssembly with mscripten. This is not the case when instead the code interacts with platform-specific APIs like Win32 on Windows or the equivalent on other platforms. In this case, the platform-specific code needs to be isolated with platform abstraction layer and dealt with. Somehow the code needs to be modified to work with WebAssembly. But the code that compiles and doesn't use a system APIs, platform-specific APIs, normally works almost immediately when compiled to WebAssembly. That can be dependencies on missing APIs or on other third-party libraries like Boost or other libraries and also these libraries then need to be compiled to Wasm, and we will see an example later. But otherwise, this is quite effective. Even large projects like LLVM and Clang itself have been compiled to Wasm, for example, and they run in the browser. And this has been done with relatively few changes to the LLVM and Clang code base. There are, however, problems with things like multi-threading C++ exceptions. When a program uses multiple threads, this is by standard not yet supported by WebAssembly, but actually it is already supported by some WebAssembly engines like V8 or SpiderMonkey, and this is also supported by itCppCon21. So code that uses the pthread API can be compiled to use web workers in a web page. And these web workers can share the same memory to a shared array buffer. This has been disabled for a while because it was considered a security issue, but should work now. Another problem are C++ exceptions, because they are also not supported by WebAssembly yet, but they also can be emulated by itCppCon21 with JavaScript code. However, the problem here is that this code is very, very slow. And this can be a problem when a program makes a large use of exceptions. So let's look at another example. Let's look at a slightly bigger example. Let's say that we want to write a small WebAssembly module that provides some cryptographic functionalities like SHA-265 hashing. And we want to use OpenSSL for this. So what should we do? OpenSSL is a large open source library. We can get it. We can try to compile it to Wasm, and it turns out that it is not very difficult to do. With a few changes to the configuration file to the compiler for the compiler, OpenSSL easily compiles to Wasm. So the result will be here a static library that is generated that contains by Clang, by itCppCon21, and that contains Wasm code. So once we have this, we can write our code, which is the normal code that would client code for OpenSSL, which initialize SHA-256 and, for example, in this case, calculates the hash for an array of bytes. And since we are in a C++ conference, we want to have C++ classes to expose this functionality with a static function using more appropriate types like std string and std vector. And this is our C++ code. But we want to use it from JavaScript. So for this, we said that itCppCon21 provides binding, and there is a set of macros that can be used to expose this class crypto and its function, and also the byte array, byte vector of bytes, to JavaScript. After we compile this, what we get is a module where that once loaded, we can create a byte vector, fill it with bytes, and then we can call a static method to a class which is visible as a property of a module object. So the module will have a crypto property which corresponds to the crypto class, and the crypto object will have a function calc SHA-256 which corresponds to the static function, and we can pass this byte vector as argument. We can we don't have, so here we can see this code in function. We type a string and we calculate the hash. We change the string, the hash will change, and so on. And this, as you can see, What is important to notice is that everything is very simple. Once once some code base can be compiled to Wasm, it's very simple to take advantage of it in your application. The code is trivial, really. Now, let's look a little more in detail how this works. How fast this works, actually. So, how fast is WebAssembly code? What happens when we load this module in an engine? Ideally, we would like to generate code as fast as the native code that is generated by the compiler when it directly compiles to native, right, to x64. This is a bit complicated to do. It's actually not what we can get. In reality, there is a trade-off between compilation time and execution time. When the module is loaded and all its Wasm function needs to be compiled into Wasm code, into native code, sorry, we need to spend time for the compilation. The more time we spend, the more optimized the code that we generate will be. But at the same time, there will be a latency and initial delay before we are able to execute this code. This is the reason why when you load web pages with a lot of Wasm code, initially there is normally a progress bar that because we need to wait for the compilation. To speed up the compilation, we can use a faster compiler that produces worse code. So there is a multi-tiered architecture with multiple compilers normally in web engines. And normally what happens is that when the module is loaded, the faster compiler, the baseline compiler, runs and compiles all the function. And so very quickly we can have code to execute, even if it is suboptimal. And meanwhile, in parallel, other more sophisticated compilers will also compile the same function, producing better code. But actually, the faster compilers is no compilation at all. We could even use a Wasm interpreter. In this case, we will not generate any machine code. An interpreter is very simple. It's just a machine that state machine where basically for each instruction jumps to a routine that executes this particular instruction and updates the engine state. However, the problem of an interpreter is that the advantage is that it can run right away without any delay, but the problem is that it's very, very slow. However, it is not, for this reason, is not really used in web browsers, but it is useful when running on small system or on systems that do not allow the generation of dynamic code, what is called the JIT of dynamic code, just-in-time compilation. Instead, we saw that we can have a baseline compiler, which generates suboptimal code. And this is also fairly simple to implement. There is a Wasm function decoder that decodes the instruction for Wasm function. And for each instruction, templated native machine code is generated, taking care of tracking the usage of the operand stack and of the registers, and basically what is generated is a bunch of native instructions very quickly. And then there is the optimized compiler. The optimized compiler, which is normally in web engines corresponds with the JavaScript optimized compiler. We know that not only WebAssembly, but also JavaScript code can be just-in-time compiled. And we can look a little more into this. So what happens when we run JavaScript code in the script engine? So there are several phases. The first phase is to parse the text of the code, generating an abstract syntax tree, which is given to which is transformed into a bytecode, which is used by the interpreter. JavaScript certainly has an interpreter, which runs normally the code, and also keep tracks on how much each function is executed, how much is block of code is executed, and which at some point it can decide that some code deserves to be optimized. And so for this, it triggers the compilation for a just-in-time compiler. And the compilation is a complex process. It's similar to the compilation from C++ to native code. So there are several steps. There is an intermediate representation. Then there are many optimization steps. And in the end, there is a code generation. And so there is all this machinery that caused the generation, the dynamic generation of native code for this function. But JavaScript is not a static language, it's dynamic. So it's possible that the code that has been compiled was assuming that a given set of types were used in this code. But this can become not true in the next execution of the function. We can call the same function passing different types, for example, for the arguments, where it was compiled assuming that, for example, the arguments were 2 numbers. What happens if we instead we pass 2 strings? In this case, the compiled code becomes invalid, and we say that the code is de-optimized, and the engine goes back to execute with interpreter. All this to say that the WebAssembly compilation pipeline use the same mechanism, use the same pipeline, but is much simplified. The Wasm decoder just generates intermediate IR representation for the compiler, for the optimization compiler, and then it uses the compiler to generate the machine code. The result is that WebAssembly it is faster than JavaScript, but even though the difference is not as huge as the term WebAssembly could suggest, because the JavaScript JIT compilers are also very effective and generate very fast code. However, WebAssembly is still better because decoding WebAssembly binary code is much simpler than parsing a lot of text code for JavaScript. There is no interpreter. Generally there is no interpreter. There is at least a baseline compiler, so the code is immediately compiled. And there is no de-optimization because Wasm code is statically typed. There is also no garbage collection because we are using the C++ heap and stack. We are not allocating memory objects that needs to be collected. And so overall, the result is that the execution is faster. And this, just to complete the picture, this is what is actually generated by V8 for the calc function that we saw at the beginning, the function that we're doing operation on 2 operands based on the operand code. And so you can see that it is looking for specific opcodes and jumping to add or a multiplication according to the code and so on. And this code, as you can see, this is the whole code for the function. It's quite compact, but probably is not as good as the code that would be directly generated by Clang compiling to directly to x64, because there is more bookkeeping anyway to run in a script engine. Almost done. The last topic that I would like to talk about is debugging. Debugging is very important, obviously, and has always been a pain point with WebAssembly. In the past, it was very difficult to debug WebAssembly code once it was compiled, running in the engine. Initially, source maps were used, the same source maps that are used for JavaScript or TypeScript, but they were not very effective because they can provide only limited debugging information. So the result was that it was possible in the past to enumerate the source files, for example, that had been used to generate a Wasm module and to set a breakpoint on a given line. And the code would actually stop at that line. However, when you were analyzing the state of the program, you could not see the value of source variables, the original variables in C++, for example, but only the value of locals, which are like registers in WebAssembly, or the value of the memory. So it would be like debugging C++ application when having access only to the state of the registers and to the memory, and not to the state of the variables. Obviously, it's quite difficult. However, Clang and LLVM can generate dwarf debug information. They do this when compiling for Linux or Mac, and so they can also do this when compiling WebAssembly. This debug information is stored in custom sections in the Wasm module, and DevTools could take advantage of this debug information to provide full source-level debugging capabilities. And they do. There is already a beta, or I don't know if it's still a beta, probably. But anyway, there is a DevTool extension for Chromium DevTools, which works with Chrome and Edge. And so what happens when we compile with Clang? We just need to pass an additional flag to enable the generation of symbols, and the resulting modules will have these symbols in a custom section, this dwarf data, and that's all for us, for the developer. Then the developer who wants to debug should install this extension, should enable it in the settings in the DevTools. And then you see we have also the value of the local variables and all the other source level information, together with the name of the function and the construct and so on. And I have a very quick demo for this. Let's see if it works. So we can open our DevTools. We have here. There is already a breakpoint. So we see that we have here a Wasm module. Right, this is the same code we saw before. We are loading a Wasm module and using it to calculate if a string is a palindrome. And we see that thanks to the debug information in dwarf format, we have the source code, not only our source code, but also the source code generated by Unscripten for the standard libraries, for example. If we set a breakpoint and we call this function, we'll see that we have the values of I, len, the string str, and so on. And this looks like a small thing, but it required a lot of work and is actually a huge improvement for the usability of WebAssembly for real debugging. Let's go back. And that was the end of my talk. So if you have any questions, let me know.
Hey, Paolo. Great talk. We have plenty of questions right now. So this means the talk was really interesting for many people. So congratulations about that. It was very, very insightful for me, at least. And so I'm inviting all the people attending the sessions on the session Remo to vote the best questions they want to handle, because I think we won't have time to address all of them. So
I will be anyway.
But you available? Yeah.
I mean, it's only 3 a.m. after all.
Yeah, it's only 2 a.m. So it's like an after party in Italy.
Exactly.
It's usually it's a usual thing. Okay, we have just a few top questions in the section Q&A. So I can start from the first one that seems to be this one. Is dynamic code loading possible? I'm thinking about plugins. This is from Claudio.
So if with dynamic loading, you mean that the web page does not know yet what code it needs to run, but will load it at runtime?
Probably
Well,
injecting
yes,
some,
yes, I think
some code or...
it's possible because you just need to load the JavaScript code corresponding and the module. Yes, there is already an API to load to load the module from the network. So yeah, there should be no problem to do
It's
this.
just a result. Okay, I
Yes.
see. No,
But then
and Claudio, if we didn't get your question right, please clarify it in the chat. Feel free to do it. In the meantime, I think we can address the next one. Is this one? Are there class wrappers, Swig, for example, that import JavaScript objects into Wasm or export C++
yes.
Wasm object to
So
JavaScript?
this is what I was trying to explain before with and bind. So let me go back to the slide
Okay, yeah.
if I can. Let me find where do I slideshow? Okay, so the slideshow. So yes, so actually yes. So here, for example, you see where was yes here you see that we have a class in C++ and we are exporting it in JavaScript using mbind. Mbind is, I mean, this is just a small case. It's much more complex than that. I can do much more. But what you get in JavaScript is this class as a property of the module, and the static method as a function of this class, and so on. So yes, it's possible with Emscripten. It will be possible probably in the future with other more standard way, but they are still planning on that. But Emscripten already works.
Nice. Okay, thanks, Paolo. Let me take another one. The next one is so what does the socket support allow you to do? Can you bind on a port from JavaScript in the browser? Can you connect to a standard socket that does not use the WebSocket protocol?
So so if this is for the Emscripten support, well, by default, WebAssembly cannot do anything. It does not even know that sockets exist. If you use Emscripten to work with a web platform API, probably you can do everything that is possible to do with JavaScript, because in the end you are calling a JavaScript function. With Wasm, instead, you are calling the operating system, but I must confess that I don't know the details, what is available in the Wasm API for sockets. We just need to check.
All right. Well, Claudio is clarifying the questions before that he asked before. I was thinking whether something like loading a plugin is possible from C++. In native programming, we use DLLs. I heard that Wasm code cannot alter code, so it's unclear if extending a module's functionality at runtime is possible.
Module functionality.
I got it
No,
now. Yeah.
currently with what we have now, no. I think there are proposals even for this. If you go to the website, to the GitHub for WebAssembly, there are a number of proposals and people working on very fancy things like coroutines, things like that. But no, I don't think it's at this moment. No.
Okay. I think we can take the last two. And the first one is generic, but I think it obviously is in the topic of WebAssembly, which is the current state of the art of trading. The current state of the art of I think it's.
From the point of view of the implementation in the browsers, I think currently it works. When there were the Spectre vulnerability, trading was disabled. The shared buffer were disabled by all the browsers, so multi-threading could not be used. But now it's been working for a while, so multi-threading for WebAssembly works for sure with V8, so in Edge and Chrome, and with SpiderMonkey, so in Firefox. I don't know about Safari, probably it does, I'm not sure. And from the point of view of the developer, you need to use script 10 and pthreads for this.
Okay.
But
Okay.
many applications like Google Earth, I think, they are relying on the fact that you can use multi-threading with WebAssembly more easily than with JavaScript, because you have this shared memory, for example, and yes.
Okay, I think we can take the last one, Paolo. Then you can follow up on the networking area. The last one is about what happens if you forget to null terminate the buffer pass to is palindrome.
Any bug in the C++ code becomes a bug when it's executed. For example, if you have an infinite loop in C++ code, you see that the web page will never end, will hang. And in this case, you can get an exception, and exceptions are transformed into JavaScript exceptions if you are running in a web page.
Nice. Okay, thanks, Paolo. I think
Thank you.
we are perfectly in time. It's 11:45, and so you can get to the networking. So I invite all the people interested in follow
Yes,
up
one more
with
question.
Paolo. On the networking area, we have the next talk at 12, so in 15 minutes. But Paolo will be here because he doesn't want to sleep, so no worries about. I remember to give feedback, so go to italiancpp.org/feedback and give feedback to this session and all the others. So thanks again, Paolo.
Thank you, Marco.
Enjoy the rest of the conference. Enjoy probably your time sleeping, and see you around, everyone. See you in 15 minutes in this track to attend Claire's talk about refactoring superpowers.
Yes.
Cheers.
Thanks.
See you.